A common theme in Spec Evo is to have a hothouse world in the distant future. This usually involves volcanoes pumping out greenhouse gases, most notably carbon dioxide, into the atmosphere, spiking the temperature. Such a scenario is often a means to give rise to a world where the ecologically dominant roles are occupied by cold-blooded or ectothermic animals, most notably reptiles. Meanwhile, endotherms, usually mammals, but to a lesser extent birds for some reason, quickly go into decline, sometimes going completely extinct, or play a much smaller role in the environment than they do now. But would a hothouse world truly lead to animals like reptiles, or assorted invertebrates, becoming the ecologically dominant species? Well, a lot of Spec Evo that employs this trope seemingly wants to make a future version of past climates, or what outdated paleontological interpretations portray them as being. The climate of the Earth has fluctuated a lot in the past, but over the course of most of the Phanerozoic, the temperature was higher than it is currently, with ice caps forming at the poles during the Ordovician-Silurian and Carboniferous Permian boundary periods. Conversely, the hottest periods were in the Cambrian, Devonian, Permian-Triassic, and the Cretaceous. The last of these occurred during the reign of the dinosaurs, and even though the rest of the Mesozoic wasn't as warm as the Cretaceous, it was still warmer than the Cenozoic. Although the Mesozoic is often referred to as the age of the dinosaurs, it's also known as the age of the reptiles, with many non-dinosaurian sauropsids, like pterosaurs and marine reptiles, filling ecologically dominant roles. Going back to the late 19th and early 20th century, it was thought that all of these animals were ectothermic. However, during the dinosaur renaissance, multiple lines of evidence were found which challenged the notion that dinosaurs were cold-blooded. From the 1960s to the 1990s, paleontologists argued long into the night as to whether dinosaurs were warm or cold-blooded. Now, in the 2000s, virtually no one is still entertaining the idea that dinosaurs were ectothermic, with the argument being over whether they were mesotherms, or partially cold-blooded, or endotherms, with more paleontologists leaning toward warm-bloodedness in recent years. Furthermore, factors like isotope composition and growth rates have indicated that pterosaurs and ichthyosaurs were also warm-blooded, with ichthyosaurs even having blubber for insulation. So, it seems that despite the warmer temperatures, the Mesozoic wasn't a world ruled by cold-blooded creatures. But what about other warmer periods in Earth's history? Well, during the Cambrian and late Devonian, all animals were cold-blooded, but that's because endothermy had yet to evolve. The Permian is a bit tricky. This period was dominated by the early synapsids, or amniotes more closely related to mammals than reptiles and birds. In the early Permian, the pelycosaurs were predominant, while in the late Permian, the more derived therapsids filled the ecologically dominant roles. But what kind of metabolism did these creatures have? One way to get an idea is to look at their modern descendants, i.e., mammals. Modern mammals are divided into two main groups: the monotremes, which lay eggs, and the therian mammals, which give birth to live young. Other therian mammals have internal body temperatures similar to ours, with the placental average being 36.5 degrees and that of marsupials sitting at 35.3 degrees, although there is still a bit of overlap between the two. Meanwhile, on the monotreme side, the platypus's internal temperature is 32 degrees, and while the echidna's average is similar, it can vary by 10 degrees either way, effectively making it a mammalian mesotherm. This suggests that earlier synapsids did have lower body temperatures than modern mammals, with possibly a degree of mesothermy. Looking at their fossils, it does appear that these proto-mammals did indeed have some degree of thermoregulation. Furthermore, over the course of the Permian, the synapsids became increasingly capable of thermoregulation, possibly starting with the iconic sailbacks such as Dimetrodon and Edaphosaurus, using their sails to thermoregulate, putting it in the sunlight to warm up, and putting it in the breeze to cool down. Even while the temperature was getting warmer, warm-blooded metabolism was being selected for in the progenitors of mammals, who were the ecologically dominant animals at the time, and, while it can be argued that endothermy would have evolved more rapidly if the climate was getting cooler, it does undermine the notion put forth in The Future is Wild that a warmer climate would dethrone the mammals, let alone virtually drive them to extinction. Strangely enough, birds seem to be doing pretty well in the hothouse world of 100 million years in the future, although this could be explained by the niches they occupy. Birds have even higher body temperatures than mammals, usually between 39 and 43 degrees. So, one would expect that they would be in an even more disadvantageous position. However, they do occupy a very specific niche, that being flyers, and, being flight capable, requires an organism to expend more energy per time and body mass unit. With their higher internal body temperatures, birds can support faster metabolic rates, which in turn allows them to expend energy faster and can give them a competitive edge when occupying airborne niches. But, going back to the mammals, if we are to understand how a hothouse world would impact them, we have to discuss how a greenhouse effect would impact global temperatures. While it can increase the average temperature by, say, 5 degrees, it won't result in an increase in the average temperatures of 5 degrees across all latitudes. The greenhouse effect doesn't just increase the global temperature, it homogenizes it. This means the aforementioned example would probably raise the temperature in mid-latitude areas by 5 degrees, in the polar regions by as much as 9 degrees, but only about 1 degree at the equator. Currently, the average temperature at Earth's equator is 27 degrees Celsius, and throughout the Cenozoic, while polar temperatures frequently vary by as much as 30 degrees, even during the hot periods, equatorial temperatures rarely exceeded 32 degrees, with 40 degrees only being observed in the greatest mass extinction in Earth's history. All this to say that a hothouse world would be one where the global temperatures most closely resemble those in the modern tropical regions. Indeed, during the Paleocene-Eocene thermal maximum, we see tropical ferns in the Arctic. Even though reptiles play a more predominant role in tropical areas than they do in temperate ones, these areas are still dominated by mammals. So, a hothouse world would certainly lead to reptiles being more abundant than they are now, but it's unlikely that they will become ecologically dominant herbivores or carnivores, globally at least. Although, there is still a possibility that they could locally occupy these roles. Even though the Mesozoic is known as the age of reptiles, there are multiple ectothermic sauropsids which have filled ecologically dominant niches in the Cenozoic. Perhaps the best example of this is the fauna of Cerrejón in Colombia from 60 million years ago. This included the iconic giant snake Titanoboa and the enormous turtle Carbonemys. In the Eocene of North America and Germany, you had the hoofed crocodile Bovirasuchus. From the end of the Cretaceous to the mid-Miocene in northern South America, you had a group of stem crocodilians known as the Sebekasuchids filling the role of top predator, while the Phorusrhacids, or terror birds, occupy this niche in the southern half of the continent. The largest of these, Baronisuchus, could grow to 6 meters in length and weigh up to 1,720 kilos, making it the largest terrestrial predator of the Cenozoic. In the immediate aftermath of the KPG extinction, the global temperature began to rise until the Paleocene-Eocene boundary, at which point it began a steady decline until we get to the Pleistocene with all the ice ages. Given that all of the aforementioned reptiles existed in a warmer time period than today, one could be led to believe that if the trend was to be reversed, we could have some supersized reptiles, which, while not as being predominant as they were during the Mesozoic, could have a profound role in the ecosystem like some of the scaly monsters of the Cenozoic. But there's a problem with this idea. Not all Cenozoic mega-reptiles lived in warmer time periods. Some lived in the Pleistocene, even lasting long enough to encounter modern humans. Upon arriving in the continent 65,000 years ago, the first Australian Aboriginals would have encountered the iconic giant ripper lizard, a supersized monitor which is the largest terrestrial lizard of all time. This animal grew to between 5 and 6 meters in length and weighed in excess of 500 kilos. There was also the large horned turtle relative Myolania, which grew to 2 meters in length. The fact that reptiles were able to occupy these niches within the past few tens of thousands of years indicate that cooler temperatures aren't inhibiting reptiles from occupying these roles elsewhere in the world. One problem for them could be the rise of the Carnivorans. In the Paleocene and Eocene, the dominant mammalian predators were the hoofed mesonychids and creodonts. However, the end Eocene extinction 34 million years ago dealt these a heavy blow, and in the aftermath, the Carnivorans, a group which includes ecologically dominant predators like dogs, cats, bears, raccoons, mongooses, weasels, and hyenas, became the dominant predators. One of the key differences between them and the earlier top predators is that the Carnivorans had bigger brains, which they employed while hunting. As such, when they became the top predators, it set a new precedent for the herbivores. No longer was being fast or strong enough to minimize their chances of becoming prey. Now, they had to think their way out of an attack, and we see brain sizes in hoofed mammals increase during this time as well, implying an evolutionary arms race had begun. If you look at the skull of a mammal or bird and compare it to an ectothermic reptile, one thing that stands out is that the brain case of the warm-blooded animal is much larger, and, with the precedent set by the Carnivorans in the Neogene, it may be that reptiles were no longer competitive in the niches they filled in the Paleogene, only surviving as long as they did in Australia because of the absence of carnivorans. We often see carnivorans like jaguars and giant otters actively hunting predatory reptiles larger than themselves like caimans and anacondas. While going after a larger predator than yourself is rare in the animal kingdom, the problem-solving capabilities of carnivorans could come into play. Reptiles are cold-blooded, so a big cat or otter could, say, learn to preferably hunt such prey in the cool morning hours, where being warm-blooded gives them a decisive edge. As such, if any reptile attempted to fill the niche of terrestrial top predator, they would face both competitive exclusion and predation pressure from carnivorans. Remember, many carnivorans inhabit equatorial regions, and with a greenhouse effect only raising the temperature a few degrees there, it's not likely they'd find the new climate unbearably hot. So far, we've only discussed worldwide climate patterns, but what about continent-spanning ones? It's predicted that some 250 million years in the future, a new supercontinent will form. Exactly how the pieces will fit together is still debated, but one scenario, known as Pangaea Ultima, would result in much of the continent being too hot for mammals, which the authors of a recent paper have argued will lead to their demise. However, this assertion is problematic. While much of the continent, about 92% of it, may very well be uninhabitable to mammals, there will still be temperate areas far from the equator and near the coastline, with temperatures conducive to mammalian habitation. But, okay, it may not wipe out all the mammals, but, with only 8% of the continent being habitable to them, certainly someone else, i.e. reptiles, will replace them as the dominant clade of species, right? Well, this depends on what criteria you use, because while in this scenario, reptiles will be dominant over the majority of the land area, this area will be composed of a barren desert with extremely low rates of plant growth. This is because with all the continents clumped together, there will be less coastline relative to the total land area. For every given square kilometer of land in this central desert, there will be far less food to sustain the herbivores, which in turn means less to feed the carnivores than there would be in the areas dominated by mammals. So, while reptiles could be dominant over a larger percentage of the Earth's land area in such a future, the overall mammalian biomass will still be greater than that of the reptiles. Instead of focusing on how a future hothouse world would impact the relative abundance of mammals compared to other animals, perhaps Spec Evo authors should explore how it would shift the taxonomic composition of mammals themselves. To understand this, let's go back to the mammalian family tree. In systematic terms, a mammalian refers to the descendants of the last common ancestor of all living mammals. Mammaliaforms refer to synapsids with traits we consider mammalian, but didn't necessarily descend from said common ancestor, with many having branched off earlier. Theriomorphs refer to all mammalians more closely related to the therian mammals than monotremes, while theriiforms are those with features we associate with therian mammals, most notably live birth, but trying to figure out who is capable of this involves a bit of guesswork. Within the therian mammals, marsupial and placental refers to all species descended from the last common ancestor of all living marsupials and placental mammals respectively. Meanwhile, metatherian refers to all therian mammals more closely related to marsupials, while eutherian refers to all therian mammals more closely related to placentals. For example, Thylacospilus was a metatherian, but not a marsupial. Leptictidium was a eutherian, but not a placental, and the multituberculates were theriiforms, but not therians. The non-mammalian mammaliaforms died out in the mid-Cretaceous, with a spread of flowering plants giving crown group mammals the edge. Meanwhile, many non-placental eutherians, non-marsupial metatherians, and non-therian theriiforms survived the mass extinction, and, while they remain common worldwide in the Paleogene, most died out in the Miocene, with some persisting into the Pliocene. Going back to the late Cretaceous, the multituberculates were the most common mammals, and the metatherians were more abundant than the eutherians. Given that monotremes and marsupials have lower internal body temperatures than placentals, using phylogenetic bracketing, we can infer that the multituberculates did as well. So, what we see is mammals with lower internal body temperatures being more common in a warmer time period. Conversely, it was likely that the cooling trend seen through much of the Cenozoic gave placental mammals the competitive edge, largely restricting marsupials to Australia and the equatorial regions of the Americas, while completely driving the multituberculates to extinction. So, if prehistory is anything to go by, instead of giving rise to a new age of reptiles, a hothouse world could instead lead to a metatherian renaissance, with marsupials being more competitive in the warmer climate. In the Americas, they would spread both north and south, and in Australia, where they are already dominant, they could spread to Eurasia as the two continents collide. In a future hothouse world, one possible scenario is that the marsupials dominate the equatorial regions, placentals dominate the polar areas, and you have a mix of both in the mid-latitude regions. Given how many examples of convergent evolution there already are between placentals and marsupials, there are seemingly endless ways to imagine what kind of forms marsupials would take should they come to become the ecologically dominant herbivores and carnivores elsewhere. One might imagine that the kangaroos and wombats could become supersized again, becoming the giant herbivorous browsers and grazers in a manner similar to their relatives in the Pleistocene. Meanwhile, the dasyuriforms like the quoll and Tasmanian devil could wind up filling the niches big cats do now in tropical areas, although they could do it in a unique way, just as the marsupial lion and its relatives employed a hunting system seen nowhere else. Meanwhile, in the Americas, opossums tend to be generalist omnivores, so they might evolve into something vaguely resembling a bear before they diversify into other megafaunal niches. In summary, the notion that a hothouse world would lead to the demise of the mammals is largely based on the idea that in such conditions, being warm-blooded is more of a waste of energy. But in tropical regions today, which the whole Earth resembled during the hothouse periods, mammals are still dominant and have internal body temperatures significantly higher than the ambient temperatures, allowing for a more active lifestyle than reptiles. Even though warmer global temperatures would make reptiles more abundant than they are now, the most profound impact it will have will likely be changing the relative abundance of the major groups of mammals themselves. If you truly wish to make a world dominated by cold-blooded reptiles, you'd be better off with a warmer seed world, and even then, one group will likely evolve thermoregulation and rapidly diversify. As always, if you enjoyed what you saw, please like and subscribe. Thanks.